1.14. So they want us to use equation 1.23, which is the probability of finding a system between 2 points A and B is given by this integral. So we need to use this equation to find the answer to part A of the example at the end of section 1.6, which is on page 15. And we need to compare it to the approximate answer found in the example. Okay, so this relates to the example problem on page 15. So for part A, the approximate answer which we found was by assuming the interval is infinitesimal, so we don't have to compute the integral. The approximate answer was obtained by computing just this, and it was found to be 4.979 times 10 to the negative 6. Now they want us to compute the more accurate answer to this question by performing this integration. So let's first write down what the wave function or state function is. It's given by a to the power negative half times e negative modulus of x, where a at time t equals 0. Now we are looking to find the particle between 1.5 nanometers and 1.5001 nanometers. So the value of psi squared is going to be times 2 e to the negative modulus of x over a is 2. Now I am going to just cancel out these 2's here. And this will give me 1 over a times e to the negative 2 of x over a. And the value of a is given to be 1 nanometer. Okay. Sorry about that. Yeah, okay. So this is the value of psi squared. Now we have to perform the integral from 1.5 to 1.5001. Value of psi squared, I'm going to take 1 over a outside because it's a constant. And modulus of x is just going to be x because we're dealing with positive values in the integration times dx. Now this will be 1 over a times the integral is just going to be this. Now we have to apply the limits 1.5, 1.5001. So this is going to be 1 nanometer times, actually, hang on. I don't think we need to plug in the value of a here because the a actually gets canceled. So let's get the negative half outside. This will be e to the power negative 2 times 1.5001 nanometer divided by 1 nanometers minus e to the power negative 2 times 1.5 nanometer divided by 1 nanometer. The units get canceled out beautifully, and we have negative half times whatever this value is. So I am going to compute the value right now. Negative 2 times 1.5001. 0.049777 1111. Negative 2 times 1.5. And this value is 0.0497877068. So if I subtract these values, 0.049777, I will have a value like this. Now, the negative sign gets canceled out. So I'm going to divide this by 2. And I end up with which can be written as 4.978 times 10 to the power 6, negative 6, sorry. And this answer is exactly, it's almost similar to, it's the same answer basically, what we had when we performed the calculation, assuming the interval was infinitesimal. So this shows that the approximation is valid and we end up with the same answer, whether we use the approximation or whether we go through the tedious computation of integral.